Okay. So when you are trying to use the electronegativities, you want this page of the reference packet with the electronegativity values. Then the table that tells you how to classify bonds given the electronegativity difference between the two atoms that you're looking at, that are bonded. And then the bottom table is going to help you find the shape of the molecule around the central atom. So we will use that today. And let's get started. So we had HF. So I redraw those molecules we did last week. I forgot to save the things. But it's just as well because we need room to do the rest now. So we had HF. We had HF. So here it's not a molecule where you will be asked the molecular geometry because it's just two atoms, and when you have two atoms, they're just bonded to each other, and there's no shape other than they're on one line, right? So here what we will do is calculate the electronegativity difference between H and F. So you want to look at that table on the left side of electronegativities. And you take the values that are for hydrogen, so here in the upper left corner, and fluorine in the upper right corner. And when you calculate the electronegativity, so it has to be a positive difference. So you take the highest value minus the smaller value. So 4.0 for fluorine, 2.1 for hydrogen. That's a difference of 2.1. Just calculating to make sure I'm not making mistakes here. So it's a difference of 1.9. So the delta En here I have is saying it's electronegativity difference, right? The E is for electronegativity, En, and then delta means difference. You're calculating a difference here. So that's a large value, and then the second step is to look at the middle table here in the reference page. And when you have an electronegativity difference and you look at the middle row between 0.5 and 1.9, and so 1.9 included here, the bond type will be covalent, which means electrons are unequally shared. They are pulled toward the more electronegative element. And the more electronegative element is the one that has the higher electronegativity value. So that means this HF bond is classified as polar covalent. I forgot to open my chat, so let me open that in case somebody is using it. Okay. So the HF bond is polar covalent, and so here it's only one bond, and it's polar. When you have a polar bond, it's good to show the polarity on the drawings. Like for example, for your lab 3, you will want to do this. Here, because it's just one bond and it's also a molecule, I will show it with an arrow, but for other structures, we'll show it with the little delta pluses and delta minuses. But here I'll do it with an arrow. And so the arrow is what we call a dipole. It shows how the electrons are pulled towards the more electronegative element. And so here, because the higher value is for fluorine and the lower value is for hydrogen, so the arrow will point towards fluorine. Let me change the color of that to red. So I'll do it like this. So it points towards fluorine because fluorine is the more electronegative element. And this means that the electrons are pulled towards fluorine. And we do a little kind of plus on the other end of the arrow, and that shows where you have the more, or I mean the less electronegative element, right? It's where you have the delta plus, you know, element. Yes, this is chapter 4. As I said, we will do the review after that at 11. So, so the bond is polar and the molecule is also polar. The HF molecule is polar because there is only one polar bond. There is nothing to cancel it. And so we can add here, we can add that, and the molecule is polar too. Oh. Right, because there's nothing to cancel the dipole moment. So then the molecule is polar. So let's do the next structure here, NCl3. So here we have a central atom. The central atom is N, the nitrogen. But we have only one kind of bond. It's the NCl. And that reminds me, I want to do the shape first. So let's go over the shape. And for this, we will use the bottom table of the reference packet. So, yes. So to determine the shape around the central atom of a molecule, you count the number of electron groups around the central atom. And here the central atom is nitrogen. And you count the electron groups. And a single bond is an electron group. A lone pair is an electron group. A double bond would be an electron group. A triple bond would also be one electron group. So here nitrogen is surrounded by 3 single bonds and 1 lone pair. So let me write this, that 3 single bonds plus 1 lone pair. It's 4 electron groups, right? 4 electron groups around N. So 4 electron groups around N, then you go to the table here, table 10.1, that shows the electron and molecular geometries. And you will find the row that says electron groups 4. And so it's the last 3 rows of this table that shows that. So, and then you pay attention to what the type of the electron groups. We have three bonds, you know, 3 atoms bonded and 1 lone pair. So you want to follow the row that has bonding group 3, lone pair 1, right? So it's this row here. The electron geometry is tetrahedral. That's the bond angle between the 4 bonds, you know, between each 2 consecutive bonds. That's the bond angle. And then the molecular geometry is trigonal pyramid or trigonal pyramidal. Because here you see you have 4 electron groups, but one of them is a lone pair, and lone pairs are not visible in the molecule shape. So it's there, it repels the other electron groups and gives the trigonal pyramid shape, but it's not, you know, visible. So then the molecular geometry is trigonal pyramid. It's a trigonal pyramid, and so I'll do the drawing now. There is a convention on how to do this, so I want you to know how it looks. So you will put your central atom N, you know, kind of on top of the pyramid. And it's nice to have its lone pair here on top to show why it will have this shape. So the convention wants that you do a straight line for bonds that are in the plane. And when you have a trigonal pyramid, which means a pyramid with a triangular base, there's only one bond that you can have in the plane. And so let's make it to the right here. And it's gonna be going downward to the right or to the left. You can do it also to the left. And then we'll put chlorine at the end here, Cl. And then the other two chlorines will be on the other side and going downward as well, but they will have what we call wedges. And so let's do one wedge. I wish I didn't have that color, but okay. So that's the way you draw wedges. So one of the wedge will be hashed, or have dashed like that, and that at the end you will have a chlorine, Cl. And so the one that is hashed like that means it's a bond that goes behind the paper plane. So it goes behind, away from you, away from the paper plane. And then the other wedge, so you do the two wedges next to each other. You can make them, right next to each other. They go downward on one side of the, and this one should be full. It's going to be hard to, well, let's try that. But, well, I won't make it full because it's going to be difficult here. And then that's where you have the other chlorine. Okay. And so this shows the that full wedge. It's not full, it's white, but that full wedge is showing the bond that comes towards you. If the paper plane, shows that straight line with the bond in the plane, then the other bonds are, one going away from you and the other one coming towards you. So that's how we draw molecules conventionally when they are trigonal pyramid. And I will expect that you do that on paper for lab 3. So that's why I want you to get some practice on doing that. So this shows the trigonal pyramid shape. Next, we need to decide if this molecule is polar. Before we decide for the molecule, we need to see if they are polar molecules. So we will need to calculate the electronegativity difference. And let me make this black. Let's calculate the electronegativity difference. I'm just doing my delta like this because I cannot do it otherwise. So electronegativity difference for the bonds that are in that molecule. And there is only one kind of bond, and it's the NCl. So you look at the electronegativity of nitrogen, it's 3.0. And Cl, it's also 3.0. So it doesn't matter which one you put first, it's all 0. When you have an electronegativity of 0, it means that if you look at the middle table here in your reference packet, if you have an electronegativity difference of less than 0.5 units, then it's a non-polar molecule. Electrons are equally shared. So here, because the nitrogen and chlorine, they pull equally on electrons, then the electrons will be equally shared between the two. And sorry. So let's finish this text. No. So non-polar bond. I should say the NCl is non-polar. I should say bond here is non-polar. And so when you have a non-polar bonds, there, you know, if your molecule has only non-polar bonds, there is no way that your molecule will be polar, right? So thus molecule is not polar. It cannot be polar because you have no polar bonds. Okay, so that that is for NCl3. Please do something in the chat if you have a question, for example. Let me draw lines here to make sure we understand what is what. This is for HF here. Oh, okay. It's a bit fat. Okay. So now let's do ONCl. Let's look at the shape of the molecule. So the central atom again is nitrogen here. And so you need to count the electron groups around nitrogen. And as I said, an electron group is either a double bond, a single bond, or a lone pair, or a triple bond. So here around nitrogen, you have a double bond, that's one group, a single bond, that's another group, and a lone pair, that's 3 groups. Or another way to count that is, you know, 1 atom, 2 atom, and then the lone pair. So let's write this down. So 1 double bond plus 1 single bond plus 1 lone pair. So that means we have 3 electron groups. Okay, 3 electron groups around N. Maybe I should add that around N. No. Around N. So what does it make? What shape does it make? So we have 3 electron groups, 2 are bonding groups, and 1 is a lone pair. So you want to look at the third row from the top. That starts with 3 electron groups, 2 bonding groups, 1 lone pair. The electron geometry is trigonal planar because you have 3 electron groups. And so the bond angle is 120 degrees. But what you see, the molecule geometry is bent because one of these electron groups is not visible, it's a lone pair. So then the molecule will look like bent. So then here bent, the molecular geometry is bent. Molecular geometry is bent. Bent from a trigonal planar. Okay, so let's draw this then. Yeah, I have to redraw it. So I'll do the central atom here, N. Give it its lone pair. I think it's good to do the lone pair only on the central atom when you are, you know, it's more essential on the central atom when you are doing the geometry of the molecule, because it really shows you why the molecule has this shape. And so it's bent, and but it's planar, right? Trigonal planar means it's all atoms in one plane. So here, the 3 atoms, oxygen, nitrogen, and chlorine, are in one plane. It's a flat structure. So because of that, we can draw the 3D structure with only straight lines, because all bonds are in the plane. But once, oops, that's not what I want. So I'll do a straight line going down And I want this to be bigger. So one straight line here for chlorine, and I'll do the double bond going this way. Towards the oxygen here. Oxygen. And the other one will be chlorine. Okay. So when you do the molecular geometry, you know, the 3D drawing, it's okay to drop the lone pairs on the outside atoms only, right? You can not do the lone pairs on chlorine and oxygen here. It's fine. However, you should do them on the nitrogen because it justifies the shape, right? So I'll leave it like this. And it shows how it's bent, and the angle here between the oxygen and the chlorine is 120, right? So that's the shape. Now let's do the electronegativity difference between the, so this time we have two types of bond. We have an NO bond and a NCl bond. We do not have an OCl bond, so you only calculate the electronegativity for atoms that are bonded. So let's do electronegativity difference. Let's do it for NO first. So electronegativity of oxygen is 3.5 and the electronegativity of nitrogen is 3.0. So that's a difference of 0.5. And so the NO bond is so you look at the middle table here, you have an electronegativity difference of 0.5. And so here it says it's included in that second row, right? It's a polar covalent bond. Bond is polar. I will just write polar. Okay, so that first bond here is polar. Let's do the electronegativity difference for the other bond, the NCl. Oh, and we have it above here. So it's, you know, nitrogen is 3.0, chlorine is 3.0, it's a difference of 0. And so the NCl bond is non-polar. Okay, so let me just do my delta here. So we have one of the bond that is polar. And the other that is not polar. So let's, I'll do an arrow in this case again. For bigger molecules, you will see it's better to do the delta plus delta minus. But here I will do an arrow and make it red. We only do arrows for polar bonds, right? And so the NCl bond is not polar, so there will be nothing there. The NO bond is polar, and it's more polar, you know, it's more electronegative towards oxygen. So the arrow will have to point towards oxygen, right? And we do a little plus on the other end to show it's where the electrons are pulled from. And the arrow shows where they are pulling, where they are pulled towards, so towards oxygen here. And so we have this polar bond here, NO, and there's nothing to cancel it, right? So what do you think? Is the molecule as a whole polar? You can answer in the chat. So do we have a polar molecule here? Yes. Yes, it is polar because there's nothing to cancel that polarity, right? That dipole, there's nothing to cancel it. The other bond is non-polar. So the molecule as a whole is polar. And so that's why I did an arrow here, because when you have a polar molecule, you show the polarity of the molecule with what we call a net dipole, which is an arrow. And the net dipole here is also the same as the dipole for the bond polarity. So they are the same. The bond polarity and the molecule polarity are the same because there is only one polar bond. So this shows the polarity of the molecule as well. Okay, so that's doing this NOCl. Let me draw lines here that we know what we're doing. One like this. Oops. Okay. Yeah, I'm thinking if I select all of this, I can move it up. Oops, oops, oops. Okay. Let me try to move this down. Oops. Oh. Okay. Yeah, we could do it like this. Okay, let's do the next one. Let's do the shape first. So the central atom here is silicon, and silicon, it's surrounded by 4 single bonds, right? So let's write this down. Oops. So 4 single bonds. That's it. It's only 4 single bonds. So that's 4 electron groups around Si. Right? We're only counting around the central atom, and here the central atom is the silicon. So that means what kind of shape do we have? So you look at the table. The table, and you want to look at a row that starts with 4 electron groups. And here it's 4 bonding groups, 0 lone pair, right? Silicon has no lone pairs and it's only 4 bonds around it. So you look at that middle row that starts with 4 electron groups, 4 bonding groups, 0 lone pair. The electron geometry is tetrahedral. And so that's the bond angle, 109.5, when you know it's a perfect structure with all atoms around silicon, for example, would be the same. Here we have chlorine and 3 hydrogens. So the bond angles may be slightly different between the chlorine and the other hydrogens than between the hydrogens together. So, you know, when you have different atoms, it can distort a little bit the shape, but it's very close to that, and that's what you would want to record. And so the molecular geometry is tetrahedral. So molecular geometry is tetrahedral. Oh, I was not typing. Oh. Molecular geometry is tetrahedral. Okay. Okay, molecular geometry is tetrahedral. So that means we will need to redraw this structure with the 3D way to do it. So there is a convention, and I want you to really remember this for your lab 3. So when you have a tetrahedron, there's only 2 lines you can put in the plane. Only 2 bonds, I mean 2 bonds. And the other 2 will be the wedges. And so you always place one of the bond that is in the plane straight up vertical towards, from the central atom up above it. So we'll place silicon here, Si, and hydrogen above. I will reposition the atoms after if needed. And you know what? I'll put chlorine here, and I'll put all my hydrogens on the bottom, and let's move this one and change it to chlorine. I'll put chlorine on top because you will see it's convenient to have it there. Chlorine, Cl. So I'll do 2 straight lines for 2 bonds in the plane, and I will do the vertical one between silicon and chlorine, and then one on the side here between one of the hydrogen and silicon. Oops. So the next 2 bonds will be wedges. Let me make them thick and black. Okay. So the wedges, you do them both on the other side. You do them next to each other, and they need to be going downward, right? You want to give the shape of a trigonal pyramid at the base of the tetrahedron. So it goes like this. You go downward, do 1 line, another one to make it a, oops. Like that. And then make it hashed. The one in the back, make it hashed. Oops. 1. So I'll make, okay, like this. And that's the bond going away from the plane of the paper. And then the other wedge just next to the first one. And this one should be full, but here it's, I'll make it white. I'll leave it like this. Right? And so this way you have that impression that you have trigonal pyramid for the, let's make this smaller. Okay. Oh. No. So that's how you draw the tetrahedral molecular geometry. Oops, oh, I was writing in the chat, I realized that now. Okay. Okay, so here again, I will tolerate that you do not do the lone pairs on the chlorine, because chlorine is an outside atom, and so it's okay if you do not do the lone pairs on it. Lone pairs should be done on the central atom if it has some, and here there is none on silicon, so we leave it like this. So we have the shape. Now let's look at the bond polarity. Do we have polar bonds? And here we have 2 types of bond. We have the silicon hydrogen and the silicon chlorine, right? So there is no need to do the difference between hydrogen and chlorine, or hydrogen and hydrogen, right? So only do silicon hydrogen and silicon chlorine. So electronegativity difference between, let's do silicon hydrogen. So the electronegativity for silicon is 1.8. The electronegativity for hydrogen is 2.1. So we'll do 2.1 minus 1.8 equals, that's 0.3. So the difference is 0.3 for the Si bond. And so you look at the second table here, electronegativity difference of 0.3 is less than 0.5 units. So the bond type is nonpolar. Electrons are equally shared between silicon and hydrogen. That was hydrogen. The SiH bond is nonpolar. So let's do the electronegativity difference between silicon and chlorine. So silicon again is 1.8, chlorine is 3.0. So we'll do 3.0 minus 1.8. It's a difference of 1.2. So the SiCl bond. So you look at the middle table, the SiCl bond with the difference of 1.8 falls into the second row here, where the electronegativity difference is between 0.5 and 1.9. And that's a polar covalent bond. So this bond is polar covalent, right? I can write that covalent, there's room. Okay, so we have one of the bonds, or three of the bonds here, the SiH that are not polar, and only one bond that is polar, the SiCl. So because it's polar, we'll draw the, again here we'll do an arrow because it's just as well. Let's make it, yeah, thick enough and red. So we'll show the polarity of the bond with the arrow between silicon and chlorine. Between silicon and chlorine, it's chlorine who is more electronegative. So the arrow should point up towards the chlorine and from the silicon. And we'll do the little plus on the other end to show that here it's lacking electrons. You know, you have a partial positive charge on the side of silicon. And the arrow is pointing towards chlorine, which shows that chlorine has a partial negative charge on chlorine. So this shows the bond polarity. Now we have to decide, is the molecule polar as overall? And again, that's another example where you have only one dipole moment, and it's not cancelled by any other dipoles, right? So that molecule is again polar. All my examples are kind of showing that. Oops. I'm trying to get in there. Okay. So molecule is polar. And again, it happens that the polarity of the molecule follows the polarity of the bond, the SiCl bond. So the dipole arrow here shows the molecular polarity again. So just so that we have an example of that, I'll show you how we draw the delta minus and delta pluses. So here you would do the delta minus on the side where the electrons are pulled towards that. And then the other delta, you know, it's lowercase delta, right? The delta we have in front of the electronegativity difference is the capital delta, and here that's the lowercase delta. And so it's a plus here. So those little deltas are really meaning a very small value, and it's a very small charge, very small partial positive charge on the side of silicon and partial negative charge on the side of chlorine. It's not full charges, right? It's not one negative charge and one positive charge. It's really a small amount. The delta is really a small proportion, much less than 0.1 out of 1, right? It's really small values. But it makes the molecule polar, and that changes the properties of molecule a lot. And so that's done for this one. Let's draw a line here to make it clear. This is for that molecule. Okay. My lines are not so straight. Okay. I hope you're still following. So we can continue with the last molecule here, which is acetic acid, actually. Okay, so that's more complicated. We have much more kinds of bonds, and the shape. So when we are trying to find the shape of a molecule that is, having more than one central atom, you will need to determine the shape around each of, potential central atom. So here, that first carbon that has 3 hydrogens and 1 carbon around it, that's a central atom, and you can find the shape around that one. The other carbon here is also a central atom, so you will find the shape around that one separately. And you can even consider the oxygen here a central atom and find the molecular geometry around it. So let's try to be organized. We'll start with the first carbon here, then the second carbon, then the oxygen. So let's count the number of electron groups around that first carbon. So that carbon is surrounded by 4 single bonds. So let's label it first C. 4 single bonds equals 4 electron groups. And when we have 4 electron groups, then you look at the table, the bottom table here, and 4 electron groups, it's one of those 3 bottom lines in the table. 4 electron groups, and these are 4 bonding groups, and there is no lone pairs on that carbon, right? So you see that the electron geometry is tetrahedral, the angle is 109.5, and the molecular is also tetrahedral, right? When there is no lone pair, the electron geometry matches the molecular geometry. But what you always have to, tell is the molecular geometry is what matters typically in questions. It's what you want to record. So 4 electron groups, which means it's tetrahedral geometry for that first carbon. Okay, let's continue with the second carbon. Around that second carbon, there's no lone pair. There is 2 single bonds and 1 double bond. But basically, you can also say it's bonded to a carbon and 2 oxygens, so three bonding groups. Either way works, right? I will write 2 single plus 1 double bond. 2 single plus 1 double bonds. So that's 3 electron groups, right? The double bond counts as 1 electron group. 3 electron groups. So let's look at the table to determine the molecular geometry around that second carbon. We have 3 electron groups, and it's only bonding groups. So it's going to be the second line here, 3 electron groups, and there are 3 bonding groups. There is no lone pair, 0 lone pair on that carbon. And so the electron geometry and molecular geometry are trigonal planar. It's a flat structure around that C, around that carbon, and the angles are 120. So trigonal planar. So this one is trigonal planar. Let's try to save some space here. Okay. Trigonal planar for that second carbon, and let's do the oxygen, because you can also do the oxygen molecular geometry. Oxygen, you know what I mean, the one that is bonded to H. So oxygen. So around that oxygen, there is 2 single bonds. So it's bonded to 1 carbon and bonded to 1 hydrogen. And there is 2 lone pairs, 1 above, 1 below. So we can say 2 single bonds plus 2 lone pairs. And that's 4 electron groups. 4 electron groups around that oxygen. So 4 electron groups. So you look at the lines where it starts with 4 electron groups, and you want to find 2 bonding groups, right? Only 2 atoms are bonded to that oxygen, and it has 2 lone pairs. So that's the bottom row, right? 4 electron groups, 2 bonding groups, 2 lone pairs, and it's a tetrahedral geometry, electron geometry. But what you see, the shape of the molecule around that oxygen is bent because you have 2 lone pairs that are not visible. And so what you see is just the bent structure, but those lone pairs, they are repelling the 2 bonds and you know, make it bent. So we can say it's bent from tetrahedral. Okay, bent from tetrahedral. So now, yeah, it's a pity it's just there. Okay, we need to draw this. That's challenging. Okay, so this is tetrahedral around that carbon, and it's flat around this one and then bent there. This OH, CO, and the other double bond CO and the CC bond, they can all be in one plane because the second carbon here has a trigonal planar structure, so all bonds can be in the plane there. And so we'll put that in the plane, and we'll make it, you know, we will do the tetrahedron for the bottom carbon, and then we'll do the structure going upward and flat for the rest of it. So, you know, it's tricky. I have to admit it's tricky, and I will not ask you something like that in the exam. Let's start with the letters here. Carbon. Carbon. I will have all hydrogens on the bottom here. Hydrogen, hydrogen, and the other hydrogen here. And then we'll have the C here. And oxygen. And so let's see, we'll position things after that. And let's make the last hydrogen here. Okay. Let me just make this narrow so they don't bother me. And you can do that on your paper while you wait for me to do it, right? Do it also yourself. So doing those 3D structures requires that you have some kind of good ability to visualize in 3D, which is not easy for everyone. So I understand if it's very challenging for some of you, or okay. So let's see, it's not straight. It's 120 degrees, so like this and like that, right? This was not well done at first. You remember that second carbon is trigonal planar with 120 degrees, so it has to be like a triangle between, you know, that central atom, the second carbon, and then the two oxygen and the other carbon. It has to look like a equilateral triangle, right? Then here it will be bent with a sharp angle, so sharper angle, so it can be like this. Okay, let's do the single bonds. Okay. So between that carbon, between the two carbons, it's a straight line, it's in the plane. Then we have this other line in the plane. This one is in the plane. And here we have a double bond. And that finishes the trigonal planar structure here, right? This is trigonal planar here. And you see how I make them all equidistant from each other, the 2O and the first carbon here. They have to be all equally spaced around the second carbon. I'll do the lone pairs on the oxygen because it helps to understand why this is bent here. It's because we have two lone pairs on oxygen here. One lone pair. Oops. Right? It justifies that shape. And I'll do the lone pair here because I don't like it when it's nude. Okay. That carbon, that oxygen also has its lone pairs. But you understand why this one is bent. The oxygen molecular geometry is bent from tetrahedral, and that's because you have 4 electron groups around that oxygen. The 2 lone pairs and the 2 single bonds. And so the 2 lone pairs are repelling the other bonds, the 2 bonds, and making that geometry look bent. Okay, now let's do the tetrahedron. So this first carbon here is a tetrahedron. Oops, I need to select line, and we'll do a single line here for that hydrogen. It's in the plane, same plane as this, right? Because it's in the same plane as the vertical bond here. And then we'll do the wedges for the other two. These are not in the plane. That's the only ones that are not in the plane. So that's the wedge, hashed wedge. That shows the bond going away from the paper plane. And I'll do the other wedge just next to it. And this one is the full one. Let me bring the hydrogens closer. That's their bond, right? And so that's the only 2 bonds that are not in the plane from that tetrahedral geometry of the first carbon. And so, okay, let's finish with the electronegativity difference now. So we have a OH bond, a CO bonds, 2 of them, CC bond, and the CH bond. I will not count the electronegativity of the CC bond because there will be the same number and it's going to be a non-polar bond. So there's no point of spending time on that. So let's do the electronegativity of the CH bond. Carbon electronegativity of 2.5 minus hydrogen electronegativity of 2.1. That's a difference of 0.4. A difference of 0.4 is considered non-polar. So from doing it a lot, you will see that the CH bond is non-polar. Next, electronegativity difference between CO. So oxygen is quite electronegative with 3.5 minus carbon 2.5. That's a difference of 1.0. And if you look at the middle table here, a difference of 1 in electronegativity difference makes it a polar bond. So the CO bond, and it doesn't matter that it's single bond or double bond, both of them will be classified the same way. And you calculate only once for the CO bond is polar. So yeah, CO bonds, from doing this a lot, you will probably remember the CO bond is polar. And the last one is the OH. So electronegativity difference for the OH bond. Electronegativity of oxygen is 3.5 minus 2.1 for hydrogen equals, let me make sure I do this. Yeah, it's 1.4. And that's the OH bond. And the OH bond is, you know, a difference of 1.4 is a polar covalent bond, is polar. Okay. So CO bonds and OH bonds are polar. You will see that a lot when you do exercises. And that's it. We said the CC bond is non-polar because it's twice the same atom. So we don't bother calculating this one. So because we have a lot of bonds that are polar, this time I will use those delta pluses and delta minuses because the overall polarity may be more complicated this time, right? So let's do the delta, and I will do that with this and make it red. And maybe sticker like this. Okay. So we said the CH bond is non-polar, so there's no need to show the delta pluses and delta minuses when you have non-polar bonds, right? Non-polar bonds, you should never have an arrow there or a delta plus and delta minus. So this is non-polar, this is non-polar, the CC bond is non-polar. Okay, CO bond is polar and it's polar towards oxygen. Oxygen has a value of 3.5 for the electronegativity, and that's pretty large. So that's going to be a delta minus here, and that's going to be a delta plus on that second carbon here, right? So the electrons are pulled towards oxygen, and then that CO bond is the same. It's polar towards the oxygen. So there's also a delta negative on that other oxygen. And then we look at the OH bond, and it's also polar, and it's also polar towards the oxygen. So we'll put a delta plus on the hydrogen side. So now it shows how, you know, it's pulling, both oxygens are pulling the electrons and depriving the oxygen, the hydrogen and the carbon of electrons. So basically there's an arrow going like this towards that oxygen, another one going towards that same oxygen from the C, and then another arrow going this way towards that oxygen. And so they will not cancel, right? those bond polarities will not cancel. Overall, it's going to be polar, and especially towards that oxygen, and also towards that oxygen. To show the molecule polarity is kind of hard. You know what? I'll probably do the arrows. So we need an arrow this way. There's another arrow that way, and a third one going this way. So they don't cancel, right? Because it's a flat structure. Maybe these two, they add up to something going this way, but then there is that one. So actually, yeah, I would not give something like that in an exam because it's really, really hard to tell which way is the overall polarity. But if you use the ChemMagic website to show the MEP, I think it's MEP, the map of the electronegativity and the polarity, you will see how it would be very red on that oxygen and very red on that other oxygen, and then very green or even blue on that side. So that's how, polarity shows up, and it's hard to show on paper. So molecule is polar because dipoles don't cancel. Okay. Do you have questions on this? I want to stop now on chapter 4.